Hey everyone, welcome back. This video is about chapter 16. So I'll go ahead and walk you through it one item at a time. Alright, so chapter 16 is about oxidation and reduction reactions, and because oxidation and reduction reactions is a bit of a mouthful, we tend to just say redox reactions, which is the words just mashed together. So redox reactions are about one thing: transfers of electrons. And that's happening in every redox reaction. One thing will be gaining electrons, the other thing will be losing electrons. The thing that's gaining, we call that reduced. The thing that's losing electrons, we call that oxidized. So when we're dealing with these, ultimately we want to just be able to define each thing as whether it's gaining or losing electrons. And the first thing is to determine what we call an oxidation number, because that's the easiest way to track whether something is gaining or losing electrons. So the first thing to do is, the simplest thing is, if something is itself an ion or is just alone, you can just look at its charge. That is the oxidation number. The rest of the principles that we'll be learning about are about basically assigning a charge to something that doesn't have a charge. So I want to actually, to do this or to see how this goes, I want to actually look at this first exercise on your worksheet. It's not hard to do. If something is by itself, you know its oxidation number because it's literally the same as its charge. So what's calcium 2+'s oxidation state or oxidation number? 2+. That's what it is. What's lithium? 0, because it doesn't have a charge. What about bromine? 0. What about phosphide? 3 negative, because that's what it is. So if it has a charge, or if it's alone and doesn't have a charge, that's its oxidation state. You don't need to do any more. You don't need to follow any rules. You're already done. Okay, but then the rest of it is where it gets a little bit more tricky. So if something doesn't itself have a charge, like lots of molecular compounds don't have a charge, or polyatomic ions have a net charge, but they don't have a charge for everything in between, then we need to be able to follow these rules to determine what something's oxidation state is. So the first thing that you do is, in my opinion, you'll find a few different rules, and they're all ultimately the same thing, but you put different weights on it or different orders a little bit. So first thing that I say to do is definitely, if it's an ionic compound, separate the ions and solve for the oxidation states of everything separately. So if we were to work on a problem where we do that, let's do barium hydroxide right here from the worksheet. Barium hydroxide. Ooh, my focus is out. There we go. All right. So the first step would be to separate barium and hydroxide, and it'll get a lot easier from there. You have these two things present, barium and hydroxide. Well, the oxidation state of barium is done. Barium's oxidation state is a +2 because that's what it is. Now we actually just need to work on hydroxide and figure out what the oxidation states of oxygen and hydrogen are in the hydroxide ion. So to do that, step 2 says to give the more electronegative element the charge that it wants to have. Or if H is bonded to a more electronegative element, you can start by giving it a +1. And we do have H bonded to a more electronegative element, so we could go either way here. And it doesn't really matter. We could start by giving hydrogen a +1, so let's go ahead and do that. The other option would be start by giving oxygen a -2. So whichever way we want to do it. So we'll start by giving hydrogen the +1. The next step, and that should say +1. And now the next step is to try to figure out what oxygen is, such that the whole thing will add up to the charge right here. So it all has to add up to -1. So what must oxygen be in order to add 1 and still get -1 out? Well, that must be a -2, which it just so happens is the charge that oxygen wanted anyway. So we would have solved for these no matter which way we started. That makes oxygen a -2 and hydrogen a +1. And we're done. Those are the oxidation states for barium, oxygen, and hydrogen in barium hydroxide. We could try another one over here. We could try CH2. It's not an ionic compound, so we can't separate the ions. we could start, in this case, just like before, it's best to start with hydrogen. So we'll give hydrogen a positive 1. There are 2 of those, so that's a total of positive 2. And the whole thing has to add up to 0 because it doesn't have a net charge. So we need to figure out what carbon will be. Well, there are 2 carbons. So what is each carbon going to be? So that if you add 2 to it, you get 0. So that, you can think about it for a little while, but that's going to be negative 1. 2 times negative 1 is negative 2, plus 2 is 0. So carbon in this compound is negative 1. Hydrogen is positive 1. So you can see it's just a sort of way of assigning charges to things that don't have charges. They're not already ions, so we're just sort of assigning them not formal, but oxidation numbers, which are like charges. Okay, so from there, once we're able to assign the oxidation states, then we need to determine whether something in a chemical reaction was oxidized or reduced. So here is our scale. The idea is if something goes down in its oxidation state in a chemical reaction, it was reduced. If it goes up in its oxidation state through a chemical reaction, it was oxidized. So let's work on the problem from the chemical, or from the worksheet. We'll work on problem C here. And I'll just go ahead and write it in on the nutshell sheet so that you can track what we're doing here. So the reaction is that HCl reacts with zinc to form hydrogen gas and zinc chloride. And we're trying to find out which element is oxidized and which element is reduced. So some of these things we can already assign their oxidation numbers. Zinc doesn't have a charge, so its oxidation number must be 0. Hydrogen doesn't have a charge, it must be 0. These ones we'll have to go ahead and work on just like we were previously. So we know that this is a neutral compound, so it has to add up to 0. Hydrogen, we start out by giving it a positive 1. And then we ask, what must chlorine be, which added to 1 would equal 0. So that must be a negative 1. Come over here. This one we can solve directly. This is an ionic compound, so in the first step we can just say that this is made of zinc 2 plus and chloride and say that those are their oxidation states, 2 plus and negative 1. So it doesn't have to be a complicated thing trying to figure out oxidation states. All right, so then we're asking the question, what was reduced, what's charge went down, and then what was oxidized. So you can see what changed here. Chloride actually was negative 1 to begin with and negative 1 to end with, so it's not changing. But hydrogen went from positive 1 to 0. Hydrogen started at positive 1 and through the course of the reaction ended at 0. Zinc started at 0 and through the course of the reaction ended at positive 2. So you can see that hydrogen went from positive 1 down to 0, so that was reduced. Zinc went from 0 up to positive 2, so that was oxidized. There you have, one element is always oxidized, one element is always reduced in an oxidation and reduction reaction. Which brings us to really the last step in this chain, and that's determining the oxidizing agent and the reducing agent. So this is often a complicated issue for students because it's kind of weird. It seems kind of opposite, and so I always stop and talk about robbers because I think that sort of makes sense the way language works, and this is the same way. When someone gets robbed, there's a robber, right? And those aren't the same people. The robber is the one that took something, and the person robbed is the one that it was taken from. So in this case, think of it like if something was oxidized, that's the person who got robbed. So if you want to find the oxidizing agent, you have to find out who else was in the room with them. Who might have been the robber. So same thing here. What got oxidized is zinc. Zinc got oxidized. So what was the oxidizing agent? And for that, we're just choosing the other reactant. So here the oxidizing agent, the agent of oxidizing, is hydrochloric acid. The agent of reducing, well, hydrogen got reduced. So what reduced the hydrogen here? That was zinc. So when we talk about when something was oxidized, it had to go through a process. So we talk about an element that went through that process that was oxidized. An element that went through this process was reduced. Then we find that element over here, and if that was the oxidized element, then we find the other reactant that was present with it to say that was the oxidizing agent. And if H was reduced, then we find the other reactant that was present to say that was the reducing agent. There you have it, oxidizing and reducing agents.